is for most everybody in here that this stuff is new. So there's a couple things we're going to look at. We're going to look at how data is distributed and what percentage do you expect to see on the right or the left of a particular data value. Do you remember when we did the flipping of the coin and I stood up here and we had that bad run, well, bad or good, depending on how you look at it. We had that run in here for the experimental probability of flipping a coin. And I don't remember what we got, but I remember it was not good. It was all heads. Okay? What did we say was wrong with my data? Not enough trials. The same can be said about when we talk about data in general. You need to be looking at large sets of data in order for the things that we're talking about to be true. If you question data with, well, what if, then you know that you're talking about a weird situation and you're probably looking at a situation where you don't have normal distribution. You don't have enough data. Okay? If you take and we line up the people in this room from shortest to tallest, there is not a huge disparity in the room. If we did it for the entire school population, there would be disparity, but not a huge disparity, but you would start to see some extreme cases. We would see that we do have some fairly height challenged people, and you would see that we have some taller people. How many of you personally know a person who is taller than 7 feet? That you have a personal relationship with? There's not that many of those people out there. Okay? So it would be rare to have somebody that you know is taller than 7 feet. When we talk about adults, when you look at an adult that is shorter than, say, 4 foot, let's say 4'10", that's also an anomaly. If you line up the people in the state of California, let's talk about adults, you are going to see normal distribution. You are going to see that there's a small number of very short adults and a small number of extremely tall adults, and then everything else is going to look like this when you look at the number of people at certain heights. If you do it by male-female, it would even be more pronounced as to what type of a distribution you have. And that distribution is called a normal distribution. It's modeled by a bell-shaped curve. And you've seen bell-shaped curves when we were graphing before. But this curve is called a normal curve, and it's symmetric about whatever the mean is, bar x. And we're going to talk about how do we figure out what that curve looks like. Your x-axis, when you put your x-axis here, you're going to start with bar x in the middle. Around bar x, you're going to do bar x plus 1 standard deviation, and bar x minus 1 standard deviation. Then from the mean, you're going to do bar x plus 2 standard deviations, and bar x minus 2 standard deviations. And then bar x plus 3 standard deviations, and bar x minus 3 standard deviations. And what you're going to see is that the vast majority of your data will be close to bar x. obviously you're going to have really tall people from continuation of my example, and you're going to have some really short people over here, but they're going to be very, very small percentages. And a normal curve looks like this. So bar x is here, plus 1 standard deviation, 2 standard deviations, 3 standard deviations on either side, within 1 standard deviation of the mean. That means if bar x is here, 1 standard deviation less to 1 standard deviation more, you're going to get 68% of your data. These numbers, you need to know them. 68% of your data will be within 1 standard deviation of the mean. 95% of all the data will be within 2 standard deviations of the mean. And 99.7% of all your data will fall within 3 standard deviations of your mean. So if you're greater than 3 standard deviations or less than 3 standard deviations away from the mean, you are in an extreme situation, whatever that situation is. If you break it up into the slices, the 68% between minus and plus 1 standard deviation means this stripe right here, this interval right here is 34%, and same with this one. It means that these two intervals from minus 2 to minus 1 standard deviation and plus 1 to plus 2 are 13.5%. And the third interval on each side is 2.35%. Anything more to the right is 0.15%, and to the left is 0.15%. You have to know these numbers. You need to know the 68, 95, 99.7, and you got to be able to break them down into these slices, because the percentages are what we're after. Things that are normally distributed, there are tons of them that occur naturally. Despite what people believe, when you give a test, if the population is large enough, you have to anticipate normal distribution. 35 people taking a test, not such a normal distribution maybe. However, when we take all of the Algebra 2 data, it's normally distributed around bar x based on 1, 2, and 3 standard deviations of the mean. There are no exceptions to this. People who feel like, oh, everybody can get a whatever in the class, yeah, that may be that you can say that we could get bar x to be a 95. And then 1, 2, 3 standard deviations from the mean, but the data will still normally distribute. And there are some of you who are going to go to some schools, in particular, the more academic school you go to, the more likely you're going to get in a situation where a professor is going to say, you know what, our data is going to be normally distributed. And if 95 is bar x, then 92 is a B, and 88 is a C, and 86 is a D, and anything below 83 is an F. And you're going to go, holy crap, because 83 used to be okay. And some of you are going to get into places where you get a 91 on a test and you got a D, because they normally distribute. How many of you ever heard about, oh, let's grade on the curve? That's the last thing you want to happen in your world. If you are a good student, you do not want to be graded on the curve. Because grading on the curve has the potential to really ruin some people. What's that? Sure. Okay. This is the numbers, these are the numbers you got to be really conscious of. 68, 95, 99.7. Now you can figure out these numbers pretty easily. You have a calculator. 68 in this slice right here, you split it in half, that leaves you with 34 and 34. That's where these come from. If you're not sure where the 13 and a half comes from, it comes from the fact that we have 95 between two standard deviations. If you do 95 and take out what's in the middle two stripes, we subtract 68. 95 minus 68 is going to give you how much? 27. If you divide that in half, 13.5 in each of these regions. If we take the 99.7 and subtract what's between two standard deviations from the mean, 95, and you subtract, what will that give you? How much? 4.7. If you divide that by 2, 2.35% here. And if you do 99.7, oh sorry, if you do 100% minus the 99.7, you're going to get 0.3, and if you divide that in half, that means there's 0.15% to the right and 0.15%, sorry, to the left and to the right. Is everyone seeing where these numbers come from? You can't just say, oh, they're just numbers, I don't need to know them. You need to know them. 68, 95, 99.7. Now, there are other books where they give you different numbers here. 68 is pretty common, but the 95 and the 99.7, I've seen different numbers in different books. These are the ones we're using. Okay? Data that changes, that varies naturally, is going to be normally distributed. No exceptions. Okay, 0 exceptions. Everybody good here? How many of you have gotten for Halloween the bag of M&Ms? The fun size bag, or even a little bit bigger bag. We're not talking about a 1 pound bag. They don't give those out. Has anyone ever gotten those or anyone not know what I'm talking about? I don't expect it. You guys don't raise your hands. Does anyone not know what I'm talking about? How many M&Ms are in the bag? How many? 12? Oh, I don't know. I don't need M&Ms. I'm asking. 8 M&Ms? The probability that you select an x value and it lies between x minus 2 standard deviations and bar x. This is the kind of question you've got to be able to realize what's going on. Here's bar x, here's bar x minus 2 standard deviations. The data that's in between those is going to be the sum of the data in the two regions. So 34 plus 13.5 is 47.5% of your data will be here. From bar x less 2 standard deviations to bar x. Here's the way the notation will be written. Your x value right here is going to be between bar x minus 2 standard deviations and bar x. And you need to be able to calculate the percentage of data in between those two values. We know that this is 13.5%, this is 34%. We're just going to add those together to get 47.5%.
Now the signs are on x always going to be less than or equal to?
That's how they do it here. Yeah. So they're going to allow you to include the boundaries for those regions, which means that bar x is in more than one region. And same with any other boundary you choose. They're in 2 regions, except for, well, they're all in 2 regions. Try your glasses. into the seated. Does everybody follow this notation okay? So far we're still looking theoretically. Between bar x minus 1 standard deviation and bar x, that should be bar x plus 3 standard deviations, I think. What's the percentage? I don't know, figure it out. Bar x minus 1 standard deviation to bar x plus 3 standard deviations. What's that? Just figure it out, let everyone have a chance to calculate it, and then we'll talk about it. This is all based on knowing these numbers. You've got to have these numbers down from these two charts right here. Ellie, what you got? Okay. So this is 83.85 or 0.8385, and this is actual numbers. They give you some ideas, milligrams per deciliter and all that, but blood cholesterol, that's what we're looking for. Normally distributed has bar X of 172 and a standard deviation of 14 milligrams per deciliter. What percent of women have readings between 158 and 186? The deal is you need to draw the picture. And if you try to do it without drawing the picture, you should get somebody to wake you up because you were having a dream. There's no way. So you want to start by looking at what does it mean to be normally distributed. So we are going to start with bar X. And what is bar X for this data? So right here, the number that goes with that is 172. Your standard deviation is 14. So what's bar X plus 1? It used to be, but after the math revolution of 1729, 186. So that's bar X plus 1 standard deviation. What's bar X plus 2 standard deviations? Listen to my question. Bar X plus 2 standard deviations. Again, this is an arithmetic deal, guys. 2 standard deviations. 200. And then 3 standard deviations. 240. Going the other way.
186? No.
Bar X minus 1 standard deviation. 158. You've been dying to say that. And then minus 2 standard deviations. 144. And minus 3 standard deviations. 130. Those are your numbers. Your graph is a bell-shaped curve, and you should slice it. And you yes.
For the test, do you want us to write in the bar X?
I don't care. It's your work.
Okay.
It's up to you, but I can't see how you can do this without it.
No, I meant like the...
I don't need to see this. I don't need to see any of this. But you should write certainly these numbers should appear.
Yeah, it does.
We all are going to know, hopefully, that we're doing standard deviations, normal distribution. Hopefully this is 34%. What's here? 13.5, 2.35, and 0.15. Then you can put the same numbers over here, 34, 13.5, 2.35, and 0.15. That'll help you answer the other questions. So when it says about what percent of the women have readings between 158 and 186, you're doing an arithmetic problem. Now, you did all the heavy lifting between 158 and 186. What percentage of the data do you expect to see? 68%. Readings higher than 200 are considered undesirable. What percent of the readings are undesirable? 2.5. You have to add both of these to be more than 200. You all right?
Got it wrong. I can't add to the. It's not working.
You're not still going with 158, are you?
I said that was 2.45.
Well,
Why not?
I guess they have answers down here. So 68 and 2.5. Anybody have any questions on that? It's extraordinarily simple, but there's a lot of little things that you need to know. The score in an exam for entrance to a firefighter program is normally distributed. In fact, all exams are going to have results that are normally distributed, like it or not. There are always A's, there are always F's. There are no exceptions. It's just a matter of how do we make it so that we don't have to give an F student an F grade. That's what public education might have. We have to realize that no matter what, it'll still be normally distributed. The good thing is we want our normal distribution to appear from 100% to 70%. We want to see our data close out around the 70 mark. We don't want data to be bar Xing around 70. We want to bar X in the 80s and then bring everybody in so that we get everyone a passing grade. Again, college might not be like that. What percent of the candidates score lower than a 160? It tells you bar X is 200, standard deviation is 20. See if you can answer these two questions right now. Raphael, what'd you get for A? Does that mean you didn't do it? What'd you get? I have no idea. I'm asking what you got. Do you know what you got?
I just got the draft.
You keep eluding my question. Did you get an answer for A? Okay. See, that would have been a great response. Looking at Michaela's response, probably not as good as what you got. A lot of pressure now.
Yeah, so
Still working on that. What does your chart look like? What's on the bottom of your chart? What's bar X? To the right, number. And to the left. So that's all you need for your curve, right? And then slice it up. And I want to know what's the percentage that are lower than 160. So I'm looking for this and this. You have to add two things together. for this one and this one, what percent do you have here? Did you take any notes? This is going to be painful. Right here? If you didn't take notes, say I don't have the notes written down. Okay, that's what I'm looking for. 2.35. This is like pulling teeth right now. How much is less than 120? Or 140, excuse me. 0.15, teeny weeny, right? So these two regions together is 2.5%. Ta-da. Grace, how about the second question? Above 220.
I got 16%.
Nice. I think my mom is over 300. She would be in one of those 0.15 percenters. Seriously? Over 300? All right, so here's kinds of questions that they're going to ask you in general. A normal distribution has a mean of bar x and a standard deviation lowercase sigma. Find the indicated probability for a randomly selected x value for the distribution. Okay, so this is the type you're going to see a question or two like this, very generic, on the test. All right. So C, this stuff is a 2 out of 10 on level of difficulty. Yeah, maximum 2. Okay? All we are doing is taking this information right here, this right here, the breakdown of percentages. That's all we are looking at. Okay? So if we do this, somewhere I can. And if I take this, is this it? So these are the numbers that you're going to do. You pick a random data entry. It's less than bar x. What percent, Ashley?
68.
Did you do problem number 1?
Yeah.
What did you write down?
50.
50% is correct. We find bar x. We want to be less than bar x. That's everybody over here. That's 34, 13 and a half, blah, blah, blah. That's 50% of the data is to the left of bar x. Yeah. 0.5 and 50% are exactly the same thing. No, you get 50%. As a decimal, 50% is 0.5. As a fraction, you can put 1 over 2. I'm perfectly content with both of those. Okay? Are you going to get that stuff out of my mail?
Yeah.
Then, greater than bar x. 50. Between bar x and bar x plus 2 standard deviations. That's these two regions. Emma? How much? Between bar x and bar x plus 2 standard deviations. Here's bar x. Here's bar x plus 2. There's no way that's all the data. 47.5, 0.475%. I'm sorry? It says from bar x, there's bar x, and bar x plus 2. in between those two boundaries? What percent is here? It says the data that you choose, the data entry you choose, is between bar x and bar x plus 2 standard deviations. This is bar x. This is bar x plus 2. We want to know what's in between those. Okay? Julia, how about number 4? Between bar x minus 1 and bar x. Did you do this one?
No.
Between bar x minus 1 and bar x. Yeah. Can you sense why my confusion is here? This is easy as can be if you know this. We're giving you one boundary on the left, one boundary on the right, and we want to know who's in between. What's the percentage or decimal in between? Okay? Arthi, how about number 5? Between bar x, oh, not even between, it's just less than bar x minus 3 standard deviations.
0.15.
Nope. Less than. X is less than or equal to.
Isn't it x times?
Yes, that's what
So
it
it's
is.
x minus.
Oh my bad.
I don't understand. This is 2 out of 10, Mr. Walker.
I know. Oh, I'm an idiot. It's not that I don't understand it. I just can't read it. All right. So we're only looking at this slice right here. How about greater than bar x plus 1? Anyone get that one? 16?
Yeah.
16. Okay? So it's all about figuring out where you are and knowing your numbers. The biggest mistake that I see happening is people, when they do this, they'll, right at the beginning, they'll make their graph, put all their numbers, and they'll make a mistake with the numbers. If you screw up these numbers, that means every answer you do, although you understand the concept, can't be right. So you've got to be very good about these numbers. All right? So now what they're going to do is we're going to talk about this thing called a z-score. And z-scores are integral. In other words, here's a z at 0, that's bar x. Z of 1, z of 2, z of 3. What you're looking at is a standard normal distribution with a mean of 0 and a standard deviation of 1. The formula below can be used to transform x values from a normal distribution with a mean of bar x and a standard deviation of lowercase sigma into z values. All right, so we're looking for finding a z-score, and this is your formula for a z-score. So if you know a value, a data entry's value, whatever that is, whatever the data is talking about, and you subtract bar x, and you divide it by the standard deviation, you're going to get the z-score for that value. In the z-score, we have a table for that. And I'm going to give you a copy of the table that you can use for your homework and your test. So here's your z-score table that I just passed out for you. And I'm going to try to show you how this works and how or what it tells you. And it's a couple of details that you need to figure out in terms of what it tells you. If z is your randomly selected value from a standard normal distribution, you can use this table to find the probability that z is less than or equal to that value. In other words, This is going to tell you the percentage of the data that'll be left of your value that you are choosing. Okay? That's really important. It's always going to give you the amount of data from that value all the way to the left. Okay? Not to the right ever. This only tells you from the left. So for example here, they're giving you z is less than or equal to negative 0.4. Okay? Equals 0.3446. So negative 0.4. Here's negative 0. And then you match it up with the first. This only goes to tenths. So it's like the old multiplication tables, which you probably never saw as a kid. And you get 0.3446. That means that 34.46% of all the data will be to the left of that entry of negative 0.4. These numbers are in decimal form. If you bounce them two to the right, they're going to be percents.
If it was plus 0.4, would you do that at the 0?
So if it was a plus 0.4, you use the positive 0, go to 0.4, and you're going to see 65.54% of your data will be to the left of that. Okay?
So z values are just saying how far it is away from Rx, right?
Right, with a standard deviation of 1, though.
Okay.
Okay? Now, notice there are two weird numbers in here. They're called your extremes. The 0.000 plus, that means a smidge more than 0. It's not 0, it's just a smidge more than 0. And 1.000 minus means a smidge less than 1. Okay, but it's already out to the 5th decimal place before you see anything. So this would be like 0.9999, and you got to go up past that 4th 9 before you see a difference.
Or maybe questions were asked, like, what's to the right of it?
Yes. So how would you find it?
That,
Like let's say that we found out that, and I'm going to use easy number for you. Let's say we found to the left was 20%. What's to the right? 80. And what word do we use to talk about that? Complement. Remember that from the probability from, it covers everything. To the left and to the right of what we're talking about is all the data. If 20% is to the left, use the complement, 80%'s got to be to the right. Okay? And that's a great, couldn't ask for a better question on this stuff. Okay? Sometimes it's easier, not only easier, but the only thing you're going to know is to the left. If they're asking for the right, you got to use the complement. So let's see if we can use an example. This is a great example. We're talking about scientists are going from an aerial survey. An aerial, yeah.
Yeah, so this is to the left of the...
Every z-score always will be to the left. And keep saying that over and over again so that you don't think that you're doing an in-between or all of a sudden to the right, especially if they're asking you for an answer for the right. You're still only going to figure out the left. So they're taking aerial surveys, which means they're probably taking a picture and counting from the picture in the plane. And they're recording the number of seals they observed during each survey, and they call that X. The number of seals observed is normally distributed, and the mean is 73 seals, and a standard deviation is 14.1 seals. Find the probability that at most 50 seals were observed during this survey. So what you have to do is calculate the z-score. And remember, the z-score is the data entry that you're dealing with, in this case 50, minus bar x, 73. They're giving you that. Divided by the standard deviation of 14.1. And they don't always come out to a nice pretty decimal, negative 1.6. Sometimes it goes on. Our z-score table is only good to the tenths. So you have to round to the 10th to use that table. You can find other tables that are more accurate to more decimal places, we're just using this table. So a z-score of negative 1.6, I think we have it here. Here's the negative 1. Go out to the 0.6, gives you a z-score of 0.0548. So that means the data to the left of that is 5.48%. So the probability that you're going to see at most 50 seals is going to be about 5.5%, 5.48%, whereas a decimal 0.0548. Either answer is good for me. I'll take the decimal, I'll take the percent. Okay? But again, at most means they're asking you for a left-hand side. Okay?
So since it's 0.6, we go to 0.6.
You mean right here? Yeah, so first you find the negative 1, that's on this side, that's the integral part. Then go across until you get to the decimal part here, and we want the 0.0548 is the z-score, which tells you the percentage of data that you're going to actually see below that. So z-scores are much more specific, whereas that normal distribution of 68, 95, 97.5, that's much more of a general, here you go, and a value of 50, which is not on one of your boundary lines. Yeah, it's somewhere in there. We just don't know where. This tells you where, and it breaks down the percentage of data smaller than. So then let's say that the question was at least. That was the one that Matt asked a few minutes ago. You can't do an at least with the z-table. So you, did I say that right?
Yeah.
At least. You do it as an at most. So you figure out whatever the boundary is, 50, do the left of that, which means if we're going to say more than or equal to 50, you're going to expect 95 or 94.52% of the data will be more than 50 seals in the picture. Does that make sense?
Yeah.
So if they throw something at you that wants data to the right, you do the data to the left and do 1 minus that, 100% minus. Okay? And that's a great question. Okay, so try this one. Find the probability that at most 90 seals were observed during the survey. So we're using the same deal, but we're going to do 90 seals. And we're doing at most 90 seals. Okay, so see if you can find the z-score. You have the table in front of you. Philip, what was your z-score?
1.2.
1.2. So when you check the table, what did it give you for your decimal or your percent, whichever way you want to go?
0.8849.
0.8849. So 88.49% of the data should be at most 90 seals. Is anyone not seeing that? If you're not seeing it, we'll do it up here. Right here, folks. Does anyone have a question on 0.8849? What did you get for your z-score? Okay, I want to know what you did for your z-score. Can you just tell me what you wrote down?
I just want to understand it.
Okay, so here's your formula. Again, where are my seals? There they are. X minus bar X over standard deviation. What number are we talking about for the number of seals in this problem? 90. So we're going to plug that in where the X is. Minus bar X. What's bar X? So 90 minus 73 over standard deviation. Standard deviation, what's the standard deviation? So that's what your formula is to get your z-score. What does that give you when you calculate? was it, 70? Thank you. Rach, what was your Z-score? Give me all the decimals just for fun. 1.2056. Okay, so then to the nearest 10, we got to say 1.2. So we'll take a look at your table and find the one on the left. My table doesn't show it, unfortunately. Do you have a one on your, which is right here?
Yeah.
Then go over to the 0.2, and what number's in that box? 0.8849. That's the percentage of data to the left of 90. So at most 90 seals. Rach? Yes, no, maybe. Do you understand this formula?
Yeah.
Do you understand how to take a z-score from that table and get the percent? Or the decimal? You sure? Then let's do it backwards. Well, if they're telling you your z-score is less than or equal to 0, that's going to be 0.5. Why is that? And the other half? Okay, so why is the z-score equal to 0?
If the z-score is equal to 0, then it means that they're trying to have you find out that, okay, bar x equals x.
That's it.
Yeah.
If your data entry that you're choosing is the same as bar x, we know that bar x takes our data and splits it right down the middle. So 50% to the left, 50% to the right. And we would expect that anyway. Okay? I guess we should. That's what that looks like. The z-score of 0 means that x and the data are the same, so 50% on each side. Okay, so now in this one you have 20 colleges. We're giving you the bar x, we're giving you the standard deviation, and we're trying to find the probability that a credit card debt of the senior was at most $3,600. Okay? Was at most $3,600. We start with bar x being 3450. What's bar x plus 1 standard deviation going to be? How much? 4625, which means that the 3600 score that we're looking at is in between those two boundaries. So we can't use the 68, 97 and a half, etc. We have to use the z-score. Lily, what's the z-score going to be for 3600?
The z-score is 3600
Did you do this? Okay, the first part meaning the z-score. Okay? That's what we're looking for, the percentage. But because it's between bar x and 1 standard deviation from bar x, we have to use the z-score. Do you have the formula for the z-score?
Yes.
Okay. Bar x. It's called the mean. Okay, so what am I going to put for this? Minus over. So see if you can get me a z-score for that. So 0.1276 to the nearest tenth, what would that be? To the nearest tenth, 0.1. So look on your table, on the left look for your 0, and on the top look for your 0.1, and that's going to give you, once again, 0.5398 means 53.98%. Yep. How many decimal places do I want? 3. I'm certainly going to want everything you can get me, which is going to be 2 places. You have never heard me say round in here, right? Other than round to 3. So don't make up your own rules. You're not alone. There's still 5 or 6 people every test doing that today. Now we did. Today's homework we got changed. This is page. Unsophisticated.
Oh, psych.
You don't want me to give you the odds? I can do all. We could, but that would be exclusive. How long could this possibly take? First hour. Subtract, divide, and then look at the table. Holy smokes.